In this section, I'd like to cover 3 topics. The first one, express one language in terms of another language. The second one, convert regular expressions to equivalent NFAs. And the third one, convert DFAs to equivalent regular expressions. Let's start with the first one. Let's say I have a language L2 and it's defined in terms of L1. L2 contains a set of strings of this format, WCW, and W is a member of L1, and C is a symbol out of this alphabet sigma 1. The meaning of L2 is, for every string W in L1, there is a corresponding string WCW in L2. So each string in L1 corresponds to a string in L2. So the size of L2 should be equal to the size of L1. If you are asked to construct a machine M2 that recognizes L2, given this language L1, then you need to define this M2 using information of M1. This M1 recognizes L1. You should not use the information of W to construct your machine M2 because this L1 can be an infinite set. There can be infinitely many strings in this L1. If you define your M2 according to this W, then you have infinite many versions of this M2. But we say M2 recognizes this L2 means M2 will accept each string in this L2. So each language corresponds to one machine. You don't define multiple machines for this language. Alright, let's check another language, L3. L3 is also defined in terms of L1. L3 has this format of strings, VW. V is any string over this alphabet, sigma 1, and W is a string in this L1. The meaning of L3 is every string W in L1 is a suffix of some strings in L3. So for each string in L1, there are multiple strings corresponding to this string. So the size of this L3 should be greater than or equal to this L1. And again, if you are asked to construct a machine M3 that recognizes L3 given this L1, then you need to construct M3 in terms of information in M1. By the way, L2 and L3 are not regular languages, so you cannot construct a DFA to recognize them. We will use pumping lemma to prove these 2 languages are not regular later on. But there are some other machines that can recognize these 2 languages. Now let's turn to the second topic. We want to convert regular expressions to equivalent NFAs. There are 3 basic forms of regular expressions. The first one is the regular expression contains a single symbol, like A. In this case, the equivalent machine has only 2 states, the start state and an accept state, and only one transition from the start state to the accept state. In this case, only string A is accepted by this machine and nothing else. Each regular expression defines a set of strings, a language. If the regular expression is equal to epsilon, it means the language it defines is the set containing only one string, which is the empty string. In this case, the equivalent NFA has only one state, and this state is the start state and the accept state. This means when you start from the start state, without reading anything, you land on an accept state. So you accept that string, which is an empty string. The third atomic regular expression is empty set. This empty set is different from the previous one, the empty string, the set containing only empty string. The empty set means it does not contain any strings at all. In this case, the equivalent NFA contains one state, which is the start state, and it has no accept state because it does not accept anything. If we can construct equivalent NFAs for these three atomic regular expressions, then we can define an equivalent NFA for any other regular expressions by using operations. Other complex regular expressions are just combinations of these atomic regular expressions with operations. Those operations are union, concatenation, and a clean star. Let's talk about the first one, union. If my regular expression is defined in terms of two other regular expressions, R1 and R2, and specifically, this regular expression is the union of R1 and R2. For example, A union B. Then we can define an equivalent NFA for A union B by taking the union of those two machines, M1 and M2. M1 is equivalent to the regular expression A, and M2 is equivalent to the regular expression B. To take the union of those two machines, we add a new start state, and we add epsilon transitions from this new start state to the start states of each machine. If my regular expression is a concatenation of two regular expressions, R1 and R2, for example, AB, then we can construct the equivalent NFA for AB by concatenating those two machines for A and for B. To concatenate two machines, we add epsilon transitions from each accept state of the first machine to the start state of the second machine. So in this example, I will add epsilon transition from 2 to 3. Then mark this 2 as a regular state. Now in the new machine, the start state is the start state of the first machine, and the accept states are the accept states of the second machine. If my regular expression is a clean star of some other regular expression R1, for example, A star. To make an equivalent NFA for this A star, we start with the machine M1, which is equivalent to the regular expression A. Then we add epsilon transitions from each accept state to the start state of this M1. After that, we add a new start state, and we add epsilon transition from this new start state to the start state of the original machine, M1. Finally, we mark this new start state as accept state. We add this new start state because epsilon, the empty string, is a member of A star, so we want to accept this epsilon. By making the start state accept state, we accept epsilon. If you don't add this new start state, then the machine you constructed only contains the strings defined as R1, 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 like that. Alright, with these 6 rules, we can construct an equivalent NFA for any regular expression. Let's go over an example. we have this regular expression AB star concatenated by A union B star. We construct the machine according to the expression from left to right. So we will construct the machine for AB star first, and then construct a machine for A union B star, and then concatenate those two machines. For the first part, AB star, we can construct a machine that's equivalent to AB, and then take the star for that. Again, for this AB, we can construct two machines. One machine is equivalent to A, another machine is equivalent to B. Then we concatenate these two machines by add epsilon transition from the accept state of the first machine to the start state of the second machine. So in this case, I add epsilon transition from 2 to 3. And I'll mark this 2 as a normal state. So in this new machine, the start state is 1 and the accept state is 4. And this machine is equivalent to the regular expression AB. Now I want to construct the star for this machine. The procedure is I add epsilon transition from the accept state 4 to the start state 1. After that, I add a new state 0, which is the new start state of my machine. I add epsilon transition from this new start state to 1, the original start state. Finally, we mark this new start state as an accept state. By doing so, we constructed a machine that's equivalent to AB star. Now we construct the second machine, A union B star. We first construct the machine for A union B, then take the star. For A union B, we separate that into A and B, so we combine those two machines that are equivalent to A and equivalent to B. We take the union of those two machines by adding a new start state and add epsilon transitions from this new start state to the start states of those two machines. After that, we construct the clean star part. Again, the procedure is add epsilon transitions from each of the accept state to the start state. So in this case, I need to add epsilon transition from 7 to 5 and from 9 to 5. After that, I add a new start state, 10, and add epsilon transition from 10 to 5. Finally, we mark this 10 as an accept state. Now we have two machines. One is equivalent to AB star, one is equivalent to A union B star. And my regular expression is a concatenation of these two parts. Now I only need to concatenate these two machines. The procedure is for each accept state in the first machine, I have two accept states, 0 and 4. I need to add epsilon transitions from these two states to the start state of the second machine, which is 10. So I add epsilon transition from 4 to 10 and from 0 to 10. After that, I mark 0 and 4 as regular states because they are not accept states anymore. Now this big machine at the very bottom is the equivalent machine to this regular expression AB star, A union B star. Of course, you can simplify this NFA. Following this procedure, you only constructed an equivalent NFA. It's not necessarily the most simplified, but you don't need to simplify the machine. Now let's go to the third topic. We want to convert DFAs to equivalent regular expressions. The general procedure is if I have a K-state DFA, I first transfer this K-state DFA to a K plus 2 state GNFA. And then I eliminate states from this k plus 2 state GNFA one by one, until I only have a start state and an accept state. Finally, we take the regular expression from that start state to the accept state in the GNFA to be the equivalent regular expression for my original k-state DFA. Now I will talk about the detailed procedure to convert this k-state DFA to a k plus 2 state GNFA. In this example, my DFA has 3 states, 1 accept state, and 1 self-loop on 3. To construct the equivalent k plus 2 state GNFA, I first add a new start state S and an epsilon transition from S to the original start state of my DFA. So in this case, I have an epsilon transition from S to 1. Then I add a new accept state A and an epsilon transition from each of the original accept state to A. In this case, I will have 2 to A with epsilon transition because I only have 1 accept state. Then I mark those original accept states as normal ones. Now I only have 1 start state S and 1 accept state A. Now we have all the states for the GNFA. Let's talk about how can we construct the transitions for this GNFA. If on a single transition there are multiple symbols, we want to convert this kind of transitions to the form with a single transition with the regular expression A union B union C, if there are 3 symbols on that original transition. Then for each state other than the start state in the GNFA, if a transition from S to R is missing, then we add this S to R with the regular expression empty set to the GNFA. After this step, there is a transition from S to every other state in the GNFA. Next, for each state other than the accept state in the GNFA, if a transition R to A is missing, then I add R to A with the regular expression empty set. After this step, there is a transition from every other state to the accept state. Finally, we add the transitions between those original states in my DFA. So for each state, R and Q can be equal to each other, but R and Q are not S or A. These R and Q are states in my original DFA. If a transition from R to Q is missing, then I add a transition with that empty set. If a transition from Q to R is missing, then I add a transition from Q to R with the empty set. If a self-loop is missing, then I add a self-loop with that empty set. So after this step, the original DFA is a complete graph. There is a transition from each state to every other state, including self-loops. For example, I have a transition from 1 to 2, from 1 to 3, from 1 to itself. And the same thing for 2. There is a transition from 2 to 1, from 2 to 2, and from 2 to 3. After these 6 steps, we have converted a k-state DFA to a k plus 2 state GNFA. So in this GNFA, there are k plus 1 outgoing edges from S, and there are k plus 1 incoming edges to A. And for each state other than S and A, there is a self-loop on R, and there are k outgoing edges from R and k incoming edges to R. Now that we have a k plus 2 state GNFA, we want to eliminate states other than S and A one by one until we reach a two-state GNFA. Now I'll talk about the procedure to eliminate one state from this GNFA. Let's say I want to eliminate state 1 from my GNFA. First, you draw the resulting GNFA structure by eliminating 1. So in this resulting graph, we have a start state S, an accept state A, and two states 2 and 3. Add a transition from S to every other state. So we have a transition from S to A, from S to 2, and from S to 3. Then we add a transition from every other state to this accept state A. So we have S to A, 2 to A, and 3 to A. Now for 2 and 3, we want to make them a complete graph. We add transitions from 2 to 3 and from 3 to 2 and self-loops on 2 and self-loop on 3. This is the structure of the GNFA with 1 eliminated. Now we compute the regular expression on each transition. After eliminating 1, my resulting graph should be equivalent to my original graph with one more state, 1. So we need to change the regular expression on each transition to accommodate that missing 1. This is the procedure. Let's say I want to compute the regular expression on the transition from 2 to 3. First, find the substructure in their previous GNFA, including 2 to 3 and 1. So we have a transition from 2 to 1, a self-loop on 1, and a transition from 1 to 3, and also a transition from 2 to 3. And you will always find this substructure in your previous GNFA. But in this substructure, we only consider self-loops on 1, not self-loops on 2 and 3. 1 is the node that we want to eliminate. So in my example, the substructure is on the right. I have a transition from 2 to 1 with empty set, a self-loop of empty set on 1, and a transition of B from 1 to 2, and a transition of B from 1 to 3, and a transition of A union B from 2 to 3. Then we need to merge the expressions from 2 to 3 through 1, because we want to eliminate 1, so we will take those expressions using 1 to my new expression. So the new expression from 2 to 3 has this form: R1, R2 star, R3, union R4. That means there are two ways to go from 2 to 3. One is go from 2 to 1 then to 3. Another is go from 2 directly to 3. So we take the union of that. And we always use this format. So in my example, the new expression would be empty set star B, union A union B. Now we simplify this expression because we have empty set. You only need to simplify the expression when you have empty set inside. The rules are: the clean star of empty set is epsilon. And if you concatenate epsilon to any other regular expressions, the resulting regular expression is that other expression. If you concatenate empty set to any other regular expressions, then the resulting regular expression is empty set. So in this case, my empty set star B is equivalent to empty set epsilon B, which is equivalent to empty set. So I have empty set union A union B. Finally, we eliminate the empty set. We have A union B. So the transition from 2 to 3 is A union B. For self loop, we follow the same procedure. So for example, I want to compute the regular expression on this self loop 2 to 2. First, I'll find the substructure in my previous GNFA. So I have 2 to 1, then to 2, and from 2 directly to 2. In my example, from 2 to 1, the regular expression is empty set, and the transition on 1 itself is empty set, and the transition from 1 to 2 is A, and from 2 to 2 is empty set. Now we merge the expressions from 2 to 2 via 1. Still the same rules. We take the union of the two paths from 2 to 2. The first path is from 2 to 1, then to 2. So it's empty set star, and A. The second path is from 2 to 2, so it's empty set. The first part is equivalent to empty set, empty string A, which is equivalent to empty set. So the union of empty set and empty set is empty set. So finally, we have this expression from 2 to 2 as empty set. Alright, so this is a procedure to compute the expression for each transition. With that structure drawn in step 1, we want to compute the expression for each transition in that structure. So that's a lot of work, and it's very easy to make mistakes. Be very careful. Now go back to the big picture of my example. I have a 3-state DFA. I converted that to a 5-state GNFA. And the first step, I eliminate node 1. The resulting GNFA now has 4 states, S, 2, A, 3. And we compute the expression on each transition according to the 2-step procedure I just talked about. I recommend that you pause this video and check the details in graph 3. Now that if you understand each regular expression on each transition in graph 3, we draw a clean version of that graph and continue with the next elimination. Next, we want to eliminate state 2. Following the same procedures, we have a 3-state graph. And I recommend that you pause this video to check each transition and each expression on it. After that, you draw a clean version of graph 4. Now we have a 3-state machine. The next step is to eliminate another state, 3. After doing so, we only have 2 states, S and A, and we have a big regular expression on that transition from S to A. That regular expression is our final answer, which is equivalent to my original DFA. Now you have gone through all these tedious steps and reached this final answer. Before you celebrate your victory, let's check if this regular expression is correct or not. We don't do a proof, we only do a string membership check. We test some strings. So the regular expression is AA union AB union B, and that plus means I have at least one copy of each member in the parentheses. After that, concatenate A, then union A. This means we can generate 2 types of strings. One is from the first part, one is from the second part, A. And this corresponds to 2 ways for a DFA to accept the strings. The first one, if we can reach state 2 directly, then we accept that string. In this case, only one string is accepted, and that's A. The second way to reach an accept state is by first reach 3 and then reach 2 from 3. Sample strings are like B, B star, A. So if I read a B, I'm in state 3. And after that, I can read any number of B's and stay in 3. And then read A to reach that accept state 2. Or I can go BAA, which means I go from 1 to 3. Then I have a loop from 3 to 2 back to 3. So after BAA, the machine is in state 3. Then I can read an A to reach that accept state. Similarly, we can read AA or AB to reach that state 3. Then reading an A can reach that accept state 2.